NumPy is one of the most important packages in Python for numerical computations and scientific computation. We'll see and motivate why NumPy is required and introduce you to some basics of NumPy. NumPy is extensively used in data science, machine learning, and AI. And actually, NumPy is used in a lot of scientific areas, not just in machine learning AI. For example, for physics, in computer graphics, lots of areas. It's one of the most powerful numerical processing libraries in whole of Python. Now, what does NumPy contain? NumPy contains objects, or it contains some representations of integers and floating point numbers. It also has containers, like it has lists and dictionaries internally built so that we can do mathematical computations very efficiently. So what NumPy provides us is basically an extension to Python for multidimensional arrays. See, I can create a multidimensional array in Python, right, using existing data structures like lists, right? I can create that, but NumPy provides us much more efficient. I'll prove that to you in a while, that NumPy provides much more efficient representations of multidimensional arrays. And mathematics, what is a multidimensional array? This is a one-dimensional array, or it's also called a vector or an array, right? So an array like this is a 2D. This is a 1D array. This is a 2D array, a matrix, right? A 2D array is like a matrix. A 1D array is like a vector or an array or a simple array. What about a 3D three-dimensional array? Three-dimensional array is like a cube. Three-dimensional array can be thought of as a cube, where you have cells in a cube, right? You have a cell in a cube and data is stored in each cell. Okay. Similarly, you can have four-dimensional arrays and so on and so forth. You can have n-dimensional arrays just the way you have 1, 2, 3. Of course, I can't draw an n-dimensional array like a 4 or a 10-dimensional array on this surface. Okay, but intuitively it makes sense. Now, what it does is its implementations, NumPy's implementations of all of these multidimensional arrays is very close to hardware, and hence it is super efficient. And it's designed for scientific computations by making it extremely convenient for us. Wherever we need a multidimensional array, it's much more efficient and much more convenient for us to use NumPy arrays. And oftentimes this is referred to as array oriented computing, just like, because array is the central data structure in whole of NumPy. So NumPy provides us an array oriented computation, and as soon as you have n-dimensional arrays, all of scientific computing, mathematics, most of mathematical operations can be very efficiently done. If can be modeled as n-dimensional arrays, and if you have a nice package which can help us do that efficiently and conveniently, it's better to use it. Let me prove to you first that NumPy is very efficient. Okay. Before we go ahead, let's see how to create a simple array in NumPy. It's very simple. There are two simple ways of creating an array. So first of all, you have to import NumPy. I'm importing NumPy with an alias of np. Now if I say np.array, and if I give a list here, remember this is a list here. What I'm giving to this is a list, right? What it creates is, it takes the list as input and it represents this list internally as a NumPy array. And when I print a, I get this. It looks like a list, but it's actually a NumPy array. Similarly, if I want to create a NumPy array of all the numbers between 0 to 9, I can just simply use the arrange function here. np.arrange10 will create a NumPy array for me with values from 0 to 9. Right? These are two simple ways. You can explicitly give a list, or you can say I want numbers between 0 to 9 or 0 to n minus 1. Those are two simple ways. Now, since I've been claiming to you that NumPy arrays are much more efficient, let me prove that to you. Okay. So let's assume I use a list. Here I'm creating a list, right? Here with this I'm creating a list, right? Within the range of 0 to 999. So this creates a list of values between 0 to 999. Now what I'm doing here in this line, I'll come to what time it is in a second. What I'm doing here is I'm computing the square of each of these numbers, See, I'm saying create a new, see what I'm doing with this here, I'm saying create a new list. This is basically creating a new list. Create a new list such that the elements of the list are squares of elements. So for I in L, See, L is my original list, right? For I in L, compute I square. This is I power 2, right? And I'm creating a new list with all the squares. That's what I'm doing here. So what am I doing? I'm basically, from here, I'm creating a list of 0, 1, 4, 9, so on and so forth, 999 square. Okay, this, from this list, I'm trying to create this list using this one line code. Now what this percentage time it does, this is a very, very interesting operator or a function, if you want to think about it that way, in Python, where it runs this operation multiple times. It repeats the same thing multiple times, and it measures how much time it took per iteration. Okay, very, very important, right? It's a very, very important thing. It says how much time on an average it took for us to do this computation. Now, when I run it using lists, see this code, I'm doing it using Python lists, the built-in data structure, right? It took roughly about 307 microseconds. This is the mean. And those of you who know what standard deviation is, it took about 17.6. And so since it has run this multiple times, it got a mean of 3.307 microseconds. And by the way, for those of you who don't know, a microsecond is 1 millionth of a second. Is 1 millionth of a second. Okay, so a million microseconds will make 1 second. Okay, while it sounds small, let's look at this, right? It took about 307 microseconds, the average time it took. In our probability and statistics and exploratory data analysis, we understand about mean and standard deviation. Forget about the standard deviation, it's not very important right now, but the most important thing is the mean, right? Now let's try to do the same operation. What did we do? We took 1000 numbers and we computed the square of the 1000 numbers, and it took us about 307 microseconds, right? Now if I do the same thing using NumPy, here I'm creating a NumPy array. Here I'm doing the same thing. Here I'm creating a NumPy array of numbers between 0 to 999, right? And I'm saying a power 2. Which means I'm squaring each of the elements in this NumPy array. And I'm also using percentage time it here. It says that it took exactly roughly the mean value is 1.35 microseconds. Now, the most important thing we have to do is we have to compare these two numbers. Just look at these two numbers. If I use lists, it took me about 307 microseconds. If I use NumPy, it took me roughly about 1.35 microseconds. This is almost roughly like 200 times more than 200 times actually, right? This is way, see, even though microsecond might seem too small, compared to NumPy's implementation of computing the exponent, the list implementation is almost 200 times slower. This is what I've been saying, that NumPy is both memory efficient and it's super fast computations. It's almost 200 times faster. Imagine doing this for a very, very large computation. What we've done here is a very, very simple computation, very, very easy computation. But even for this simple and easy computation, NumPy was 200 times faster than lists, right? So I hope with this, you're convinced, with this simple experiment, you're convinced that NumPy is both memory efficient and it provides us extremely fast numerical operations. Now let's look at, with that behind us, now let's understand how to create NumPy arrays. It's very, very simple. Let's look at how to create a one-dimensional array. We just saw this, right? So I can create a NumPy array by giving a list of numbers. Once I give a list, it creates an array. If I just say A, it doesn't say it's a list, it says it's an array, which means it's a NumPy array. Now I can find the number of dimensions. This is a one-dimensional array, right? So if I say a.endim, it gives me 1, which means it's a one-dimensional array. I can also ask for the shape. So this has what? This has 4 elements, right? So for a one-dimensional array, it simply gives the shape to be 4 elements with nothing on the other side. So it just says there are 4 elements, right? Now we'll see where shape is useful when we go a little longer. I can also say length of A, which tells me how many elements are there. Now let's go to 2-dimensional and 3-dimensional arrays. So if I want to create a 2-dimensional array, which is a matrix, right? If I want to create a matrix like this, right, which is a two-dimensional array, right? All I have to do is I have to give a list of lists. Look at this. This is a list. This outer thing is a list. This inner thing is also a list. So if we create a list of lists, NumPy will take each list as a row. This it will take it as a row. This it will take it as a row. And it creates this two-dimensional array, as you can see here. Now if I say a number of dimensions, since this is a two-dimensional array, it will say it is a two-dimensional array. And shape here, how many rows are there in this? There are two rows. There is row 1 and row 2, right? So there are two rows. And how many columns are there? This is column 1, this is row 1, and this is row 2. This is column 1, this is column 2, and this is column 3, right? And it has 3 columns. So it will say that the shape of this matrix or the shape of this NumPy array is 2 by 3, 2 comma 3. Okay. Now if you say length of b, it returns the size of the first dimension, right? So look at it. Now if you say length of b, that's the difference between shape and length. Shape tells you we have an array like this, right? We have an array like this, which is 2 rows and 3 columns. This is how we write it in matrix notation. In matrix notation, at the end of this matrix, we say this is the number of rows and this is the number of columns. This is the standard mathematical notation of doing it. You might have come across this in your 11th grade or 10th grade when you're learning about matrices. Length of b basically gives me the size of the first dimension, which is 2 here, or the number of rows. Okay, now how to create 3-dimensional arrays. So we learned about 2-dimensional arrays, right? Now let's see how to compute 3-dimensional arrays. So here I have my lists, right? These are 2 small lists, and this is a bigger list, and this is the biggest list. So I have list within a list within a list, right? If you think about it, because this is the innermost list, this is a second layer of list, this is a third layer of list. So I have list within a list within a list. When I create this, what happens actually is it creates a 3-dimensional array. It creates a 3-dimensional array for me. And how does that array actually look like? It has 0, 1, 2, 3. I need to show it to you in 3D. It's a little tricky. Okay, let me try to do that. 4, 5, 6, 7. Okay, roughly that's how it looks. Okay, it's basically like a grid. It's like basically like a 2 cross 2 grid. Let me try to draw this better like this. Okay, here I have 0, here I have 1, here I have 2, here I have 3, here I have 4, 5, 6, and 7. Okay, this is like a 3-dimensional array, right? Because I have values at the vertices of each of the vertices of my cuboid here. This is like a 3-dimensional array. Now if you say what are the number of dimensions, it says 3 obviously. And if you ask for the shape, it says it's a 2 cross 2 cross 2. Okay, and when you say shape, remember what you get is a tuple. You get a tuple stating what is the size of this. So because it has 2 rows, 2 columns, and the depth of 2, right? It has length of 2, breadth of 2, and depth of 2. That's why it says it's of size 2 cross 2 cross 2. Now you can create, instead of 3-dimension, you can create 4-dimension or 10-dimensional arrays. And we'll come across these types of arrays in machine learning, especially when we're learning about deep learning. Okay, so by the way, for those of you who are interested, a 2D array is called a matrix. A 2D array is called a matrix, right? A 1D array is called a vector. Now the question is, what about an n-dimensional array? What is it called? Where n is 3, 4, 5, or any such number. It's called a tensor. These are called tensors in mathematics. Okay, so for those of you who are wondering, the word TensorFlow, that Google is very famous software from Google for deep learning. This is where the word comes from. Right? A 1D array is called a vector, a 2D array is called a matrix, an n-dimensional array in mathematics is called a tensor. Okay, so that's a new term if you didn't know about the term tensor. Now, since we have learned about how to create NumPy arrays, let's go and understand some more ways of doing it. So arrange, we have seen this function, right? If I say np arrange, if I give a value of n here, it creates a numpy array of values between 0 and n minus 1. Very simple way. The other way for us to create numpy arrays is this. This is a very interesting way. I can say that I want to create a numpy array. So this is called the start, this is called the end, and this is called the step size. So with this, what happens is it creates a numpy array with the start value being this and the end value being just less than this. Not exactly this, exclusive of this. We'll see. Step size equals to 2, which means now instead of, see, in the previous case, whenever I said np arrange 10, I would get 0, 1, 2, 3, so on and so forth up to 9, right? So here I have a step size or difference of 1 between every consecutive number. That's what is called as a step size. Here I have a step size of 2, which means my first value will be 1, my second value and my first value will differ by 2 because my step size is 2. Okay, then my next value will differ by 2, my next value will differ by 2, my next value will differ by 2. Till the time I reach 10, but I'll never put 10 in this array. Okay, it's exclusive of this value. It's exclusive of this value with this step size. Simple way, right? That's how you can create a numpy array. There is another way called linear space, which you can use to create numpy arrays, which is also very, very useful. Suppose if I want to create a numpy array, again, start, end, and here I'm saying number of points. So here I can say that I want to create a linear space. And what is a linear space? Let me explain you. So it's saying between 0 and 1. So I take this as 0, I take this as 1. Right? This is my start and this is my end. And when you're using the linear space function or linspace function, the third parameter is the number of points, not the step size. A lot of people get confused. Okay, if I want 6 points here, what I'll try to do is I'll try to divide this line into 6 equal points. Okay, now if my first point is 0, my second point will be 0.2, my third point is 0.4, my fourth point is 0.6. Now look at it. This is my 1, 2, 3, 4, 5, 6. I have 6 points and the distance between each of these points is 0.2. That's what a linear space means. It's breaking up this whole area, this whole region into equal spaced regions. And whatever are the values that you get here, it will put it in an array. Okay, this is what linear space function does. You can give it a starting and ending point and you can say between these two numbers, but including these two numbers here, right? I want 6 points and it will do that for you. Okay, now if you want to create, there are other types of very simple common arrays that you might want to create. So imagine if I say np ones 3, 3. Remember, this is a tuple now. Here, this is the function. This is the function arguments, right? And the function argument is a tuple. When I give this, what it will do for me is it will create a two-dimensional array where all the values are equal to 1. Right? It's creating a 3 rows and 3 columns. It's creating 3 rows and 3 column array where all the elements are equal to 1, because you're saying np.ones. Similarly, if you say np.zeros, it will create a 3 cross 3 array or 3 cross 3 matrix where all the elements are 0. Right? Now let's go and see something slightly different. So there is something called an identity matrix in mathematics. An identity matrix is a matrix where the diagonal elements are 1. So these are called the diagonal elements. Okay, because they're diagonal to the matrix, right? While all the non-diagonal elements are 0. Those of you who studied basic matrices in your 10th or 11th grade would immediately recognize this. Okay, so this is called a diagonal of a matrix. Anything which goes from top left to bottom right. That's called a diagonal. Now I can say np.i 3. So this matrix is represented mathematically as I 3 cross 3. Whenever you say I or identity matrix 3 cross 3, it means a matrix where the diagonal elements are 1 and everything else is 0. That's what this exactly returns. Similarly, now I can say np.i. Now I can say np.i 3, 2. It will return a matrix like this for me. okay, where this diagonal elements go from top right to bottom left, right? So these diagonal elements are 1, everything else is 0, right? Very, very simple. We use identity matrices a lot in mathematics, and you'll come across this identity matrix when we do machine learning and data science extensively. Now comes how to construct. So there's something called a diagonal matrix or a diagonal array, right? What it means is whenever I say np.diagonal, and here I'm giving a list, what it does is it creates a two-dimensional array for me where the diagonal elements, where these diagonal elements are the values that you've given here. Everything else is 0. All other values are 0. If you notice, only the diagonal elements are whatever values you give here. So if you give 4 values, it creates a 4 cross 4 matrix with the diagonal elements being equal to that, right? Extremely simple. Now if you want to print the diagonal elements of a matrix, that's also very simple. Now here I have a matrix A where the diagonal elements are 1, 2, 3, 4. If I say np.diagonal A, because for matrix A, I'm asking it the question, what are the diagonal elements? It will return me a numpy array with all the 4 values. Extremely simple again. Excuse me. Sorry. So now let's see how to create random numbers, because sometimes, actually a lot of times in machine learning, we will have to create random arrays and random matrices, because there is some powerful properties of random matrices and random vectors that we'll learn later. But what I can do here is I can say np.random.rand. Okay, this is the function and this is the package it is in. If I say np.random, np is your numpy package, right? Random is your sub package and rand is your module. Random is your module, rand is your function. Now if I say np.random.rand4, it returns me an array. It returns me an array of size 4. This has 4 elements, right? And these elements are random numbers. We will learn in exploratory data analysis and in probability and statistics that there are different types of random numbers. This random number is called a uniform distributed random number. There is another type of random number called a Gaussian distributed or a standard normal variate. If you want those values, because there are different types of random numbers. Okay, whenever we think of random number in general, we think of it as uniform random variable. If you do not understand what uniform random variable or what a Gaussian or a standard normal variable, please check out a chapter called probability and statistics, where we explain what these are, right? And if you do not understand, it's okay. Just remember that you can create random numbers using np.random, either the function rand or rand normal, which stands for rand_n. Okay, if you've already gone through a probability and statistics chapter, this should be easy. If you have not, you'll understand what these 2 types of random numbers generators mean when we learn probability and statistics. Okay, having said that, okay, let's understand some more details of NumPy, because as I told you, NumPy is extremely important. Okay, so look at it like this. Whenever I say np.arrange 10, okay, what it's creating is a NumPy array going from 1 to 9, right? Now I can use this attribute, which is a.datatype. D type basically means data type. What it tells me is the data type of this NumPy array is integer 64-bit. But if I want float, I don't want integer values, I want a float. Then what can I do? When I'm creating my array, I can just say d type equals to float. And whenever you have d type equals to float, you have your numbers represented with a dot. What this means is 0 point basically means 0.0, or 8 point basically means 8.0. Okay, so here I'm saying my data type, I want it to be float instead of int. So it's a 64-bit float here. So your numbers will actually, when you print it, it actually puts a dot here. So whenever you see this dot, it means it's a float. If you don't see it, it means it's an int when you print it. Okay, very simple. Now you can, so a couple of caveats here. So if you have np.zeros3, whenever you're using the zeros or the ones functions, it always creates a float data type, not int by default, right? because ones and zeros are often used for mathematical computation, where you're preferable, it's better for you to use float instead of int. Now let's look at some very interesting data type. So I can create a NumPy array with complex data type here. These are complex numbers. Those of you who come from areas like physics, or you might have learned about complex numbers in physics or mathematics in your 11th and 12th grade, or electronics. A lot of these fields actually use complex numbers a lot. In machine learning, we don't use it a lot, but it's good to know that there is a data type called complex. So if you say d.data type, it actually creates a complex data type, which is a special data type in Python, in NumPy. Now you can also create a Boolean. You can also create a Boolean NumPy array just like this, or you can create a string NumPy array, right? So when you say what is the type, it says S6. Now what does S mean? You can just go and see here. B is for Boolean, I is for signed integer, S is for string, right? So whenever it prints this, you can actually understand it using the simple code. Of course, you can go to the Python documentation to understand all the basic data types. Here is the link to the Python documentation. Now, having learned all of this, how to access elements in a Python array or a NumPy array, right? Suppose imagine if I have a NumPy array like this. This creates an array from 0 to 9. Now when I say A5, it returns me the fifth value. So the indices always, just like in C, C++, this is my first element, my second element, my third element, fourth element, fifth element, so on and so forth. Okay, my indices or my locations start from index 0, not from 1. Okay, it's very, very important. The first element is not at index 1, it's at index 0 or location 0, right? Now, similarly, if I create a diagonal element, if I create a diagonal matrix, here what I'm creating a diagonal matrix 1, 2, 3, 0, 0, 0, 0, 0, 0, right? Now, if I say what is the value at A2, 2, which means second row, this 2 basically means the row, this basically means the column. So second row and second column, the value is 2. Oh, sorry, my bad. So second row, second column. This is 0th row, first row, second row. This is 0th row, first row and second row. My mistake, sorry. Right? So 2, 2 means row 2 and column 2. And the value will be 3 as it's printed here. Sorry, my bad, my mistake. I stay corrected. Okay. Having done that, now let's go and see what is... okay, let's look at this. This is very interesting. So we have a diagonal matrix of 1, 2, 3, which means we have 1, 0, 0, 0, 2, 0, 0, 0, 3. And this index is 0, this index is 1, this index is 2, this index is 0, this index is 1, this index is 2. Rows. This is row 0, row, okay, sorry, column 0, column 1, column 2. Now if I can say 8, 2, 1 is 5. So what is second row? R2 is this, right? And 1, column 1 is this. So I'm saying this value, change it to 5. I'm assigning a value here. I'm saying R2 and column 1. Change it from whatever value it is, assign value 5 here, right? So I basically put 5 here. And this is what I get, right? Very simple. Now that's how you assign a value to a NumPy array. Now let's look at related stuff called slicing. Slicing is a very useful thing. So for example, if I have a NumPy array like this with numbers going from 0 to 9 sequentially, I can now, this is interesting, I can now get a sub array of this by doing something like this. So I have 3 values here, right? The first value is called the start index. The last value is called the end index. The third value is called the step. All of them are separated by a column. Okay, very, very important. All of them are separated by a column. So when I say this, what happens is it takes the first element. So this is at index 0, index 1, index 2, index 3, 4, 5, 6, 7, 8, 9. These are the indices, right? So I'm saying start with the first index, which means take this value. But instead of stepping, here I'm saying that my step size is 2, right? Which means now step 2 elements. Take the next element. Step 2. Again, step 2. Up to the 8th element, but without including the 8th element. Now, if I take step size 2, I go to 9, right? So don't take that. So this is my start, this is my end, and this is my step size. When I do that, what is the sub array I get? I get a sub array, right, of 1, 3, 5, and 7, which is what you get. When you print this, you get 1, 3, 5, 7 as a sub array, right? Very, very simple. So this is a very, very interesting form of getting sub arrays the way you need, right? Now, similarly, if I say, let's look at a slightly different operator, right? Here, when I say np.arrange 10, I have basically 0, 1, 2, 3, so on and so forth up to 10. Sorry, up to 9. Right? Now I can say a 5 colon. If I leave this empty, it means up to the end. Up to the end of the array. So here what I'm saying here is change from the 5th element to the last element. Make all the values equal to 10. So this is my first 0th element, first element, second element, third element, fourth element, fifth element, 7, 8, 9. So what I'm doing here is from 5th element up to end, change all the values to 10. And that's what it has exactly done. Right? Very useful. Now this is what my array A contains. Now I can do some more interesting things. Here I'm saying B equals to np.arrange 5. So what does B contain? 0, 1, 2, 3, 4. 5 elements, right? Literally. Now, if I do this type of indexing, so when I say B colon minus 1. So what does colon here mean? It means from the start, because I left it empty, right? From the start or from 0. Here I left it empty, which means end, which means the length of the array. Here I'm saying minus 1. What minus 1 means is, see, when I said 2 or when I gave any other value, it is basically stepping in this direction, right? If I gave it 2, it would step to 2 steps, right? Now when I give it minus 1, it will step in the reverse order. So minus 1 basically means the reverse order here. Now what B colon minus 1 is equal to, basically take this array and process it in reverse order. This will create an array which is 4, 3, 2, 1, 0. This is what it will create. Now I am saying A 5 colon, which means from the 5th element onwards, I want this to be equal to the reverse of B. Right? So from 5th element onwards, I want it to be, so what it has done is, it has taken this reverse value, it has copied it here. Right? Here, this is how you get reverse, and this is how we assign. We saw the assigning part. Right? This is a slightly more complex line, but it's important to understand. Okay. Now there's an interesting method in which all these subarrays are stored using copies and views. Okay, let's look at it. It's again not very, very complex. Imagine if I have a numpy array. I have a numpy array here of from size 0 to 9, from value 0 to 9. And when I say colon 2, it means from start to end with a step size of 2. So it will create this subarray for me. Now here is the fun part. And this subarray, I'm storing it in B. Right? So there is this function called np.shares memory. Now A is one array, B is another array. Now what's actually happening when you're doing this slicing, what's actually happening is, in the memory, it is storing, in the memory, A is, this is in your RAM, right? This is in your RAM. In your RAM, A is pointing to this. Now what it actually does is, for efficient space, B also points to the same location, but not to the same array. It points to the subarray. So B now is this subarray. This subarray is basically this element, the 4th element, so on and so forth. So internally, for memory optimization, NumPy points to the same memory location, but using something called a view. So view basically means I'm not creating a copy of the array. Instead of creating a copy of the array, I'm using some other methodology, so that the methodology is called creating a view, such that I'm being space efficient, so that I don't copy the same thing and I eat up space, right? So how can you check whether they're taking the same space or not? You can just use the function np.shares memory. If you give two arrays, it returns true, which means they both are sharing the memory. Literally, they're sharing the memory. Okay. So when two variables of different names share memory, they're probably sharing it using the concept of views. How it is internally implemented is beyond the scope of this class, because for that you'll have to see how NumPy's designers implemented views internally. There are multiple techniques on implementing views. Okay, now let's do a slightly different thing. Now I have, because A and B are pointing to the same memory location, if I say B0 equals to 10, okay, and if I print B, my B used to be 0, 2, 4, 6, 8, right? Now I changed my B0 to 10. So my B looks like this, but my A also will get modified. My A, when I print now, is no more 0, 1, 2, 3. It's basically 10, 1, 2, 3. Because A and B are pointing to the same location in memory. And hence, if you modify B, your A also will get modified. This is a very, very important thing, because you might imagine that only B will get modified and A will not get modified. No, if you're slicing, A and B share the same common memory space, and hence you'll find this. What is the workaround? If you want to force a copy, you can say that, okay, I want this, and if you say, use the copy function, then if you say shares memory, they don't share memory anymore. So when you do the copy function, A will point to its own location, C will point to its own location. If you want to force a copy, right? Now if you change C, A will not get changed as you expect. Here I'm changing C0 to 10, but my A0 still remains 0, right? So if you want to force copy, you can do it using, you can do it using copy function. Now here is something called a fancy indexing. This is actually very, very interesting. Imagine if I have some random numbers. Okay, suppose if I have some random, again, this is another form of creating random numbers. Okay, so what this says is create random numbers in the range of 0 to 20, and I want 15 such numbers. So you have 15 random numbers here, and all these numbers lie between 0 to 20. Now I can create something called a mask. Let me explain what mask is. Now here, look at it. This is a Boolean expression. I'm saying if A percentage 2 equals to 0. Now all of this is in an array called A. A percentage 2 equals to 0, and I'm equating it to something called as a mask. Now if I say A mask, what happens is it will evaluate this logical expression on each of the elements here. Okay, it'll evaluate. So what does A percentage 2 equals to 0 basically mean? It means that the values have to be even numbers, because only for even numbers the modulo 2 operation returns 0. This is called the modulo operation or the remainder, right? So when I say A mask, what it does is it applies this mask operation, this Boolean, it evaluates the mask Boolean operation on all of these values, and wherever it returns true, only those values will be kept here. Rest of them will not be kept. For example, I'm saying extracted from A equals to A mask. When I print extract from A, what I get is basically all even numbers. So you can actually create a sub array. You can actually create a sub array using masks. And what masks do is masks create copies and not views, which means it's like a deep copy, the way we have dot copy function. Masks will not create views. Okay, that's important to notice. Now there is another way of creating a mask. Now remember, look at the use of mask actually. Now I can say A mask equals to -1. What happens now is all the even numbers will become equal to -1. So this is one way for me. If I want to say take all even numbers and convert them to -1, I can create this mask the way we have shown earlier, and I can say A mask equals to -1, right? Similarly, let's look at this. There is another form of indexing that we can try. It's called indexing with an array of integers. Suppose if I have a NumPy array, right? I'm arranging 0 to 100 with step size 10, right? Because it's an np.arrange. So I have values 0, 10, 20, 30, so on and so forth. Now I can create an array. I can create a new array like this, right? It's an array in which here I'm giving a list of indices. So I want the second index, third index, and second index repeated, fourth index, and again second index repeated. When I do this, what I get here is, this is my index 1, index 3, 4, 5, 6, 7, 8, 9. So I'm saying index 2. Index 2 is 20, so it creates value 20 here. Index 3, it takes this 30 and creates here. Again index 2, so again 20. Index 4, 40. Index 2 again, which means 20. Right? You can repeat these indices. There will be instances where you have to do this. right? Similarly, of course, I can also assign new values. I can say a of, remember here I'm putting this in a list here. I want a9 and a7 both to be assigned a value of minus 200, right? Then I can put this in a list here and I can say a7 and a9, I want them to be assigned a value of 200. This is another way to do it. So with this, we have gone through a lot of operations. I know this has been a quite a long video, but I wanted to go through all the operations that are available in NumPy. And these operations, NumPy we will use extensively, I promise you. And as we have seen, NumPy is a very, very efficient, both in terms of memory and in terms of speed for doing operations on multidimensional arrays.